Today we look at the whole computer at one level, what the parts are and how they connect. You do not need any background. How a computer works. You open a program and 1 second later its window is on your screen. From your side, that is the whole event. It feels like nothing happened. A lot did. 3 questions. First question. Where was that program 1 second ago? Not inside the processor. It was sitting on a drive doing nothing at all. Second question. What moved and how far? Something had to carry that program from the drive to the part that runs it. That trip costs time. Third question. Why does one machine need so many separate parts? Why not build one big chip that does everything by itself? One picture answers all 3. We will build it, then explain it, then follow your click across it. It is simplified as it has to be, but nothing in it is invented. Every part is real. We start with the board. This dashed outline is the motherboard. Everything else plugs into it, and it carries the wiring between the parts. First, the CPU. CPU is short for Central Processing Unit. It is the square chip that drops into a socket on the board. Inside it are the cores. A core is one worker that runs program instructions. A modern chip has several cores side by side. Next to them sits the L3 cache. Cache is a small, very fast memory placed close to the cores. Each core also has its own smaller L1 and L2 cache. Then the memory controller. It drives the memory chips, and it sits on the CPU chip itself. And this is main memory. It holds gigabytes, and it is about 100 nanoseconds away from a core. A nanosecond is 1 billionth of a second. It is built from memory modules, the sticks you push into slots on the board. Your running programs live in here. The memory controller and main memory are joined by the memory bus. Every access that reaches main memory travels along it. The CPU also holds the PCIe root complex. PCIe is short for PCI Express. It is how the CPU reaches plug-in devices, over sets of wires called lanes. 16 lanes run to the first device, the graphics card. The graphics card is almost a small computer of its own. It carries a GPU, which is short for Graphics Processing Unit, and its own memory. Right beside the GPU, the picture labels it VRAM, short for Video RAM. From the card, a cable runs out to the monitor, DisplayPort, or HDMI. The monitor is the only part of this picture you normally see. 4 more lanes run down to the drive. This is a solid-state drive. It holds terabytes and it keeps them when the power is off. The picture calls it an NVMe drive. That is short for Non-Volatile Memory Express, the set of commands the CPU uses to reach it over these lanes. One more link goes down to the input-output hub, a second chip on the board. The picture calls that connection a platform link. Intel calls it DMI, short for Direct Media Interface. AMD uses PCIe lanes for the same job. From the hub you get your USB ports, for the keyboard, the mouse, and external drives. And the network interface, over a cable or over Wi-Fi. Below the board is the power supply. It turns wall power into the steady low voltages every chip on this board needs. One last thing about this picture. It is a desktop with a separate graphics card. Many computers do not have one, and use graphics built into the CPU itself instead. Now let's follow one real launch. From your click to the window on screen. It takes about 1 second, and in that second work moves across almost every part of this picture. This is one path through the machine, and a common one. You click a program icon. The mouse sends a few bytes into a USB port. USB is a family of standards, not one connector. Each device says what kind of thing it is, so the system talks to it through the right driver. The network interface sits beside the USB port. Your click came in over USB. A file you download would come in through here. Both reach the board through the same hub. That is why the hub is here. The CPU gives it one link, and it fans that link out into many ports, so you can attach more devices than the CPU has lanes for. Your click travels up that one link to the CPU. The picture calls it the platform link. A core is already running the operating system. That is software, and it is already sitting in main memory. It reads the click, works out which icon you hit, and decides to start that program. But the program is a file, and all the operating system has is a name. Its file system turns that name into a list of numbered blocks on the drive. Those block requests leave the CPU through the PCIe root complex as NVMe commands. The drive is never told the file name. They go down 4 lanes to the drive. More lanes carry more data every second, and the drive gets 4 of them. The drive's own controller reads those blocks out of its flash chips. This is the slowest step of the trip. The controller sends the data back over the same lanes and places it in main memory itself. No core copies the bytes. That is direct memory access. The device writes memory, and the core stays free to do other work. The bytes still ride real wires. They come back over PCIe to the CPU's memory controller. Only the last hop from there out to the chips uses the memory bus. And the program is here. That is what loading a program means, getting it off the drive and into main memory. Why move it at all? Reaching the drive takes tens of microseconds. Main memory answers in about 100 nanoseconds. A microsecond is 1,000 nanoseconds, so the drive is hundreds of times further away. A core cannot work at that distance. So a program runs from memory and rests on the drive. Memory forgets. When the power goes off, everything in it is gone. The drive keeps your files with no power at all, and it holds far more of them. They are also made in different ways. Memory chips, processor logic, and flash storage each need a different manufacturing process. One process cannot do all 3 well. And you want very different amounts of each. Gigabytes of memory, terabytes of storage. One chip that big would cost too much, run too hot, and could never be replaced on its own. That is why this picture has separate parts. Now a core can start running the program. A core does its work in fractions of a nanosecond. But the program is out in main memory, about 100 nanoseconds away across this bus. In that time, a core could have finished hundreds of instructions. It can carry on with other work for a while, but not that long. That is why there is a cache. Cache holds copies of what the cores are using, so most accesses never make that long trip. L3 is the big one, a little slower, and in the design shown it is shared by all the cores. L1 and L2 belong to 1 core each. A smaller number means closer and faster. As the core needs them, small blocks called cache lines are pulled in. The one it is running from ends up in that core's own L1. Which other levels keep a copy depends on the design. So the core works through the program's instructions. It keeps several of them moving at once, but the result you see is the same as if it had done them strictly in order. Drawing the window is a different kind of work. The program calls a graphics library. A driver writes the drawing commands into memory, and the graphics card is told there is work waiting. The card fetches them itself, over 16 lanes. A CPU has only so many lanes to give. A stream of frames is far more data than one file read, so the card gets 16 and the drive gets 4. Why a processor of its own for this? A GPU is not a faster CPU. It is built for throughput. Many small arithmetic units grouped into compute units, all kept busy at once. That fits drawing pictures. A screen is millions of pixels, and huge numbers of them need the same kind of work. Different groups handle different parts of the frame. The finished picture is assembled in the card's own memory, one frame after another, right beside the GPU. Same idea as the cache. Keep what you are working on close. The display engine on the card reads each frame out and sends it over the DisplayPort or HDMI cable. The window appears. About 1 second has passed. That is the trip. Mouse, hub, core, drive, main memory, cache, core, graphics card, screen. Everything on the board ran on power from that one supply. The monitor sits outside the board with its own power. One more thing. That was a cold start the first time you open the program. Open it again straight away and it may touch no storage at all, because the operating system may still be holding the file in main memory. One picture, 5 jobs. We can sort every part we named into one of them. Computing. The cores run general programs. The GPU runs huge amounts of similar work at the same time. Remembering right now. Cache and main memory hold what is being used at different distances from the core. Both forget the moment the power goes off. Remembering for later. The drive is slower to reach and much bigger, and it keeps your files with no power at all. Talking to the world. The PCIe lanes, the platform link, the input-output hub, USB, the network interface, and the cable out to your monitor. And carrying it all. The motherboard connects every part and the power supply feeds them. That is one way to sort the parts, and it is the one we use here. It is not the only one. If you study this further, you will meet 5 classic components: input, output, memory, data path, and control. The two line up. Computing is their data path and their control. The data path does the work. The control says what to do. Textbooks often put those two together and call it the processor. Remembering now and remembering later are both their memory. A textbook counts those two as one. Talking to the world is their input and their output. That is 2 more of theirs. Carrying and power is the one we added. Their 5 are all about handling information. The board and the power supply handle none of it. They carry and feed the parts that do. But every part in that picture is still a closed box. We named them and we placed them. We never opened one. Next time we open the biggest one. We go inside the CPU, look at a single core, and see how it turns a row of bits into real work. See you there.